happens when a weight is placed on a trampoline? It causes a depression. Place a marble on the edge of the trampoline and we find it tracing the curvature of that depression until it strikes a weight.
Roll it with the velocity and we find it revolving around the weight before losing energy and ultimately falling into it.
In high school, we learned that gravitational force is this intrinsic property of mass which allows bodies to attract each other.
Newton had explained this model mathematically but had failed to articulate the mechanism of exertion of this force. But hope was renewed in 1915 when Einstein postulated his theory of general relativity, coupled with a string of the most bizarre equations to explain this mechanism of exertion of gravitational force through his exemplary gravitational wave model.
Now I want you to visualize our previous experiment when I say that gravitational waves are ripples in the fabric of space-time.
Think of free space, the nothingness that I'm swimming through, the interminable voids between planets, solar systems and galaxies as the rubber sheets on the trampoline. Massive bodies like the Sun creates depressions in this fabric of space, allowing planets to revolve around it. Hold on a second there. But according to an experiment with a trampoline, the orbiting bodies eventually lose energy and fall into the void at the center. So, why don't the planets just fall into the Sun and burn? What we normally don't realize is that the planets are traveling at tremendous velocities perpendicular to the gravitational pull of the Sun, allowing them to continue revolving around it.
Imagine you're in a speedboat. The mass of the boat and its velocity is proportional to the size, velocity and durability of the ripples created around it. Similarly, accelerating masses create ripples in the fabric of space. That means like whenever I, Gangnam Style or, land a few kicks in the air, hey! I'm actually creating ripples in the fabric of space. Well, on the side of that coin, these waves that I create are virtually undetectable and their wavelengths and effects negligible.
Scientists like Weber, Jertzenstein, Pustervoit had produced the basic postulates of laser interferometry, a possible method for the detection of gravitational waves around 50 years ago. LIGO, which is the Laser Interferometry Gravitational Wave Observatory, had been set up in 2002 by the National Science Foundation and to this date has spent over $500 million to develop the equipment to detect these waves. The gut-wrenching efforts of these scientists had finally reaped fruit on 14 September 2015 when they detected the first gravitational wave. Using the highly advanced equations of Einstein, their origins were traced back to a historic collision of two black holes which had occurred over 1.3 billion years ago.
This ostensibly niche field of science is still in its budding stages. Once we begin to venture onto more audacious, far larger experiments, we'll be able to detect gravitational waves on a more regular basis. The thing is, we really don't have a clue about what we're looking into. Gravitational physics can actually redefine physics. For example, gravitational waves obtained from different time periods can actually give us information of the universe during those periods. For example, gravitational waves from about like 400,000 years from the origins of the universe can give us the long-awaited information about the origins of the universe. So like I said before, this budding field has the capability to redefine physics, answer the age-old mysteries, and perhaps unveil dozens more.